Hey there, we're going to try to get some gas laws down here real quick. We're going to start off with Boyle's Law because that is usually the first gas law people start off with. Boyle's Law is P1 V1 equals P2 V2. So what we're going to do is we're going to color code this. I'm going to use my highlighter and I'm going to put orange for the ones. And we'll go ahead and put this light bright green here for the twos. All right, and that way we'll keep track of our givens as we go along. All right, so we have an oxygen supplier who wants to reduce the volume of her oxygen tanks. She plans to take the oxygen from her 155-liter tank. Hey, let's call that V1 and store it in a 95.5-liter tank. Hey, that's a V2, right? And we just have to make sure we're going to match these things up right. So we'll keep going here. If the oxygen in the old tank, that's the 155 tank, has a pressure of 8.27 times 10 to the third kilopascals, so that is a P1 there. Right, does that make sense? You have to group them together the way they go. What will be the new pressure, right? And we're going to assume the temperature is constant because this is Boyle's Law, not the combined gas law. All right, so let's look and get our givens down here. So our P1 was 155 liters. Let me change the font here a little bit. 155 liters. And the, I changed the font and I wrote in the wrong spot. So the volume is 155 liters. There we go. And the pressure is 8.27 times 10 to the third kPa. All right, that looks good. And then our new volume is 95.5 liters. All right, for you guys who like to color code again, these were our orange. This was our green, and we're missing this here. So our unknown is the pressure in tank 2. All right, we're going to set this up, and the equation's right above there, so I'm just going to set this up as P1 V1 equals P2 V2. So 8.27 times 10 to the third times 155 equals P2 times 95.5. All right, now we have this set up like this, and we're just going to use cross multiplication. And remember, I have the fancy iPad, so I can just do this. All I'm going to do is try to get P2. Where's my highlighter? I'm going to try to get P2 by itself over here. So I need to get the 95 to the other side of the equal sign. Now, I normally would just punch it in my calculator to the other side, so I need to divide it, right? So in this case, with this pad, since you guys are all online here, I'm going to take it across the equal sign, whoop, and put it on the bottom of the fraction. So I find out that 8.27 times 10 to the third times 155 divided by 95.5 is equal to... I do not have a calculator in this room right now, except on my iPad. So it's equal to the answer to this question. All right, so you can punch that in yourselves. I don't want to spend all my time looking for a calculator. Okay, I am back with a calculator, and I already punched the answer in. So I just got a 13,422.5 kilopascals, or 1.34 times 10 to the third. Or 1 times 10 to the fourth, if 1.3 times 10 to the fourth kilopascals if you have it in scientific notation. Okay, Boyle's Law, pretty straightforward. Algebra simple. Let's move on. Charles' Law. Okay, now Charles' Law is dealing with, where's the equation? Okay, I don't have it on here, so I will put it on right now. So Charles' Law is V1 over T1 equals V2 over T2. Okay, so again, we're going to highlight this as we go. A soda bottle is flexible enough that the volume of the bottle can change without opening it. If you have an empty soda bottle, the volume of 2 liters the volume of 2 liters at room temperature, 25 degrees Celsius. What will be the new volume if you put it in a freezer at -4? So this is V1 is 2 liters. T1 is 25 degrees Celsius. And then we have T2 is -4 degrees Celsius. And we're solving for V2 in this case. All right, now, first thing, we're in Celsius. You have to be in kelvins for this to work. So we're going to add 273 and convert that over. Is that 298? And then plus 273, and that's going to be 269, right? Okay, and so we have to have that in kelvins because remember that Celsius goes below 0. Negative kinetic energy? I don't think so, right? So either there's energy or there's not energy. There's not negative energy. And so we have that going on there. So we're solving for V2. V2, T2 equals V1 over T1. Okay, now, whatever you're solving for in these equations, put the thing you're trying to find on top of the fraction. Just flip the whole thing over. In this case, the V's are already on the top, so we're good to go. But we're going to solve for V2 now. All right, now, algebra-wise, if you want to do this beforehand, you're solving for V1, so you're going to get that T2, and you're going to get, oops, I missed the top of my T, and you're going to take him and you're going to move him to the top. Like, I call it cross multiplication. I don't know what the kids are calling it these days, but that's what we used to call it. And so you're solving for V2. All right, so we have 2 times 269 divided by 298. That's all it is. Now, what's going to happen? That volume's going to get smaller, right? Direct relationship. So hopefully this is a smaller answer. I know it's going to be already. And I got 1.8 liters. Okay. Easy peasy. All right, now we have a similar type thing. And this time, we're solving for temperature. So I want to do one where we're solving for temperature, just because the algebra. So we have 280 liters, or 280 milliliters was changed to 125. So let's put that 280 for V1. And we'll call the 125 milliliters V2. If the final temperature was -155, final temperature, -55 degrees Celsius. What's that? You want to change that? Okay, we will. So it's 218 K. All right, there we go. Now we're solving for temperature. Now, easiest way to do this, again, put the T's on the top this time. So T1 over V1 equals T2 over V2. In math, remember, as long as you do the same thing to both sides of the equation, you can do that. So we flip both sides over. All right, now let's plop this thing into where it goes. All right, we're trying to get V2, or T1 on the side by itself. So let's take out V1 and whoop, don't shrink on me. Slide up here. There you go. Remember, there's a 1 down there. All right, so we have 218 times 280 divided by 125. All right, let's see what's going to happen here. The volume went down, so the temperature should go down, right? All right, 218 times 280 divided by 125. Oh, I'm sorry. The volume went bigger, so I said that totally backwards. Okay, so 488 I was right. The volume did go down, but they gave us that smaller volume already. So the temperature was higher and it went to lower. I'm sorry about that. And there we go. I got 488. Okay, this is a combined gas law question. It says we have a 20-liter container that's filled with helium and the pressure is 150 atmospheres and the temperature is 30 degrees. How many 5-liter balloons can be filled with a temperature of 22 degrees Celsius and an atmospheric pressure of 755? Well, I'll tell you what we're going to do. We're not going to find out how many 5-liter balloons we can fill. We're just going to find out the volume at that new temperature. Okay, so that's what's going to happen here. Combined gas law is P1 V1 over T1 equals P2 V2 over T2. Okay, and we're just going to get this in the right position. So we have 20 liters, and the pressure is 150. That's in atmospheres. And the temperature is 30 degrees Celsius. We're going to have to change that, so let's add 273, and that equals 303K. Volume 2. Volume 2 is what we don't know. P2. P2 is in 755 mmHgs, millimeters of mercury. Doesn't have the Hg on there, but I'm sure that's what that means. And the temperature was 22 degrees Celsius. So we better change that temperature. 295K, right? All right, now here we have one issue that we have to take care of. We have to have consistent labels, and we have atmospheres and millimeters of mercury, so that's no good. We got to change one of them. It doesn't matter which one you change. I'm just going to use a quick factor label table here, and I'm going to change this one just because the only reason I'm changing this one is because I have more room to write here. That's the only reason. It doesn't matter which one you change, right? So 760 millimeters of mercury is equal to 1 atmosphere. If you were going to change the other one, you just have that would be flipped around label-wise. All right, I do have to get a calculator out for this. And let's see what we got. So I'm taking 755 divided by 760, and I'm getting 0.99 atmospheres. All right, I'm ready to roll. Trying to find V2. All right, so finding V2. V2 is right here. So I'm going to try to get those other things by themselves. Remember, you want to cross the equal sign and get over there and take it to the top. So if it's on the bottom, take it to the top. If it's on the top, take it to the, come on, take it to the bottom. And there's our algebra. There's our new equation. All right, now all we have to do is sub in. So T2 was 295. P1 was 150, big pressure. T1 was, or V1 was 20. Divided by the temperature, 303. T1 was 303. And then finally divided by P2, which was our 0.99. And there we go. Again, multiply the tops, divide the bottoms. So when I punch this thing in, I'm just going to go 295 times 150 times 20, divide by 303, and here it comes again, divide by 0.99. If you do that in your calculator, you don't have to use parentheses, you don't have to rewrite anything, it's a lot cleaner and a lot prettier, and I'm getting 2,950 liters. Okay, now if I really wanted to find out how many balloons, video. Never mind. Okay, I'm doing the ideal gas law problem. I'm sorry, that other paper had the wrong problem on it. It wasn't a real problem. So let's look at these problems as we go. I don't even have the problem here. All I have are some numbers. First thing you always have to do is check for label consistency. We have to have atmospheres. We have to have liters. We have to have moles. And we have to have kelvins. So we need all those labels to match up with the R that you're using. So 0.0821, remember we solved that out for those labels. Okay, putting this into the equation. PV equals nRT. We're solving for T. So we're trying to get T by itself. So all we're going to do is take this nR and slide it down here. Oops, and draw a line between there. And we have it PV equals PV over RT. PV equals... Okay, let's try that again. PV divided by NR equals T. There we go. So we have to have 5.6 times 12 divided by 4 divided by 0.0821, and that will get you your temperature in kelvins. That's all it is. There's nothing real tricky about those. Usually you guys like those the best. And it equals 204.6 kelvins. All right, I'm calling that a paper. I have some editing to do in this because I had some interruptions, but it shouldn't take that long.